Among all the objects scattered throughout the cosmos, planets, stars, nebulae, and galaxies, none provoke as much fascination and unease as black holes. They are invisible, unreachable, and overwhelmingly powerful, yet their influence reaches across immense distances. For decades, they existed only as strange solutions to equations, mathematical ghosts that many believed nature would never allow to exist. Black holes began their story not in space, but on paper. In the early 20th century, physicists struggled to understand gravity at its deepest level. Classical laws could describe how objects moved, but not why space itself seemed to guide that motion. A new way of thinking emerged, one that replaced invisible forces with geometry. Space and time were no longer rigid backgrounds. They could bend, stretch, and curve under the influence of mass. This radical idea transformed gravity from a force into a consequence of curved spacetime. From this framework came an unsettling implication. If mass could curve space gently, then enough mass compressed into a small enough region could bend it catastrophically. The equations did not forbid this, they demanded it. A boundary would form, a point beyond which escape became impossible. Light itself would be trapped. Time would slow, distort, and eventually lose meaning. The result was a theoretical object so extreme that even its own creator struggled to accept it. At first, black holes were dismissed as curiosities, mathematical tricks with no place in reality. Many believed nature would always prevent such perfect collapse. Stars, after all, burned with enormous energy. Their internal reactions pushed outward, balancing gravity's inward pull. Collapse, it was assumed, would always stop somewhere short of total destruction. But assumptions began to fail. As astronomers studied the life cycles of stars, a pattern emerged. The most massive stars lived fast and died violently. When their fuel was exhausted, the outward pressure that had supported them vanished. Gravity took over completely. In the most extreme cases, nothing remained to halt the collapse. The star's core imploded, compressing its mass into an unimaginably small volume. A black hole was born, not by accident, but by inevitability. Still, proof remained elusive. Black holes emit no light. They announce themselves only through their effects on nearby matter. For years, skeptics argued that alternative explanations could account for every observation. The idea of a region from which nothing could escape seemed too radical, too destructive to fit comfortably within the natural order. Then, the universe began to speak indirectly. Astronomers discovered intense sources of energy blasting from seemingly empty regions of space. X-rays poured out where no visible object could be found. These emissions behaved as though enormous amounts of matter were being heated, accelerated, and torn apart by gravity far stronger than any star could produce. Something invisible was feeding, something compact, massive, and relentless. The evidence grew slowly, piece by piece. Invisible companions tugged at visible stars. Orbits revealed hidden mass. Radiation betrayed violent processes occurring just beyond detection. Each clue pointed toward the same conclusion. Black holes were not theoretical oddities. They were real, common, and active. What had once been dismissed as impossible was now unavoidable. Black holes were no longer just endpoints of dying stars. They were engines, objects capable of converting gravity into extraordinary energy. Matter falling toward them, heated to millions of degrees. Accretion disks formed, swirling at speeds approaching that of light. Jets erupted, blasting particles far into space. These were not passive graves of matter, but dynamic systems reshaping their surroundings. And, as discoveries accumulated, an even deeper mystery emerged. Black holes did not merely exist within the universe. They appeared to play a role in structuring it. They influenced how stars formed, how galaxies evolved, and how matter was distributed on the largest scales. Some were small, born from single stars. Others were vast beyond comprehension, anchoring entire galaxies at their centers. The universe, it seemed, was not complete without them. What began as a mathematical anomaly had become one of the most important discoveries in modern science. Yet despite decades of progress, black holes remained fundamentally unknowable. Their interiors were sealed behind event horizons. Their origins were partially hidden. Their ultimate fate remained uncertain. They challenged not just observation, but understanding itself. This is the beginning of that journey, the path from disbelief to discovery, from equations to evidence, a journey into objects so extreme that they bend space, slow time, and force us to confront the limits of what can ever be known. The first real hunt for black holes did not begin with a camera pointed at darkness. It began with a new kind of listening, an attempt to catch the universe in the act of moving. Because a black hole, by its very nature, hides the thing everyone relies on: light. If you cannot see it directly, you must learn to read what it does to everything around it. And what black holes do is disturb the world. They tug, they twist, they heat, they shred. They leave fingerprints on stars, on gas, on time itself. The problem for scientists was simple but cruel. The fingerprints were subtle, and the universe is full of noise. For centuries, astronomy had depended on one messenger: electromagnetic radiation, visible light, radio waves, infrared, ultraviolet, X-rays, gamma rays. All of it was the same language, just different pitches. That language brought humanity a detailed sky map, planet by planet, star by star. But black holes were like silent criminals. If they did not want to be found, they could almost always remain unseen, unless they fed. Feeding changes everything. When a black hole pulls in gas and dust, that matter does not fall neatly like a stone. It spirals. It forms a disk, an accretion disk, like water circling a drain. As it tightens inward, friction and violence rise. Particles slam into each other at breathtaking speeds. Temperatures climb to millions of degrees. That heat produces X-rays so intense they pierce through cosmic distances. So the best place to look for a black hole is not the black hole itself. It's the chaos around it. That realization became possible only after two discoveries widened humanity's senses. First came strange radio signals from the sky, mysterious waves that were clearly not coming from ordinary visible stars. Then came something even more unsettling. The universe was full of X-rays, blasting from places where ordinary telescopes saw almost nothing at all. Suddenly, the sky looked different. What once appeared calm, quiet points of light against black, was revealed as a violent landscape. Invisible engines were burning somewhere out there, and the heat they produced was too extreme to come from normal starlight. Something was accelerating matter into disaster. Among the first and most famous of these X-ray beacons was a source in the constellation Cygnus, the Swan. It was catalogued plainly, almost innocently, as Cygnus X1, a name that sounded like a file number. But behind that file number was a mystery powerful enough to reshape modern astronomy. Because Cygnus X1 seemed to be screaming in X-rays while hiding its body from view. To solve it, astronomers did not try to photograph the invisible. They tried something more clever. They looked for a dance partner. In space, many stars are not lonely. They are paired. Binary systems locked in orbit, spinning around a shared center of mass like two skaters holding hands. In such systems, one star can betray the presence of the other without ever revealing it directly. A star moving around an invisible companion shifts in color as it comes toward us and then away again. That shift is not imagination. It is physics. The Doppler effect. The same effect that changes the sound of a passing siren changes the wavelength of starlight. Approaching light shifts slightly bluer, receding light shifts slightly redder. A star's spectrum becomes a confession. A young astronomer studying Cygnus scanned star after star looking for this subtle wobble. And then, finally, he found it, a bright star whose light rhythmically shifted as if it were circling something heavy. But the companion was missing. No second star appeared in the spectrum. No ordinary light was coming from the object doing the pulling. Yet the visible star's motion made one thing certain. It was trapped in a gravitational relationship with something massive, something dark. The key question became, how massive? because nature has an escape hatch. If the unseen object was below a certain mass threshold, it could be a neutron star, an incredibly dense stellar corpse, but still a thing with a surface, still an object that could, in theory, exist without becoming a black hole. But if the unseen object exceeded that limit, if it weighed more than about 3 suns packed into a tiny region, then nothing known could hold it up. Then it had to be a black hole. So astronomers did what astronomers always do. They measured motion, calculated gravity, and tried to weigh the invisible by watching what it moved. Early estimates suggested the dark object might be several times the mass of the sun, perhaps even around 6 solar masses or more. That was a dangerous number. Not because it was dramatic, but because it was decisive. It meant the universe had likely produced a real black hole close enough to be studied. Yet the scientific community did not celebrate immediately, because extraordinary claims attract a storm of skepticism. And skeptics had a reasonable point: distance. Measurements were uncertain. If the star was closer than believed, the calculations could change. If the visible star was brighter or dimmer than expected, the hidden partner's mass could drop below the critical line. So Cygnus X1 became a battleground between two ideas. Either it was the first confirmed black hole, or it was a mistake dressed up in wishful thinking. Even famous physicists joined the tension. The debate grew so intense that it turned into a public wager, a scientific bet about whether Cygnus X1 was truly a black hole or not. It was partly humor, but underneath the humor was fear. Because if black holes were real, then the universe contained places where physics as we understood it began to break. And if a black hole was real in Cygnus, then it meant something bigger too. Black holes were not rare accidents. They were a natural outcome of how massive stars die. And that meant the Milky Way itself could be littered with them. Millions of invisible corpses, silent until they fed. But Cygnus X1 still needed a final verdict. To settle it, astronomers had to do something brutally difficult: measure its distance precisely so the mass could be calculated with confidence. The method would rely on geometry older than modern physics, parallax, the same depth trick your eyes use to see the world in 3 dimensions. But on interstellar scales, parallax angles are so tiny that they become almost absurd. It would require a network of radio telescopes spread across enormous distances, acting together like a single Earth-sized eye. Only with that precision could the universe be forced to admit what it was hiding. Because in the end, the truth about black holes does not arrive as a single dramatic image. It arrives as a tightening noose of evidence until denial becomes impossible. And Cygnus X1 was the first place where the noose began to close. The final proof did not come quickly. In fact, it took decades, long enough for doubt to harden into tradition. Cygnus X1 remained a suspect under surveillance, watched but never fully convicted. Astronomers knew something was there, but in science, almost certain is never enough. The breakthrough came when distance, one of astronomy's cruelest uncertainties, was finally nailed down. Using a worldwide network of radio telescopes acting as a single planet-sized instrument, scientists measured the tiny parallax shift of Cygnus X1 as Earth orbited the Sun. The angle they detected was unimaginably small, yet precise enough to settle the matter. The system lay about 6,000 light-years away. With that distance fixed, the equations could no longer escape their own logic. The invisible object weighed roughly 15 times the mass of the Sun. That number changed everything. No neutron star could survive at that mass. No exotic alternative fit the data. Gravity alone ruled the verdict. Cygnus X1 was a black hole, real, nearby, and actively feeding for the first time. A black hole was not just inferred, it was understood as a physical object shaping its surroundings in measurable ways. And what it revealed up close was nothing like a silent void. Around the black hole, gas stolen from a nearby blue supergiant star formed a blazing accretion disk. The disk churned like a cosmic furnace, particles racing at nearly half the speed of light. Collisions heated the material until it glowed in X-rays, announcing the black hole's presence across the galaxy. Some matter fell inward and vanished beyond the event horizon. Some was violently rejected, flung outward in tightly focused jets that blasted energy far into space. These jets were baffling. They erupted perpendicular to the disk, narrow and relentless, as if the black hole were not merely consuming matter, but organizing it, sculpting chaos into structure through forces no one fully understood. Magnetic fields twisted and locked into place, channeling violence into beams that pierced the interstellar medium. Cygnus X1 was no passive corpse. It was active, dynamic, dangerous, and it was only the beginning. As astronomers found more systems like it, a startling realization took hold. Stellar mass black holes were common. Every generation of massive stars left behind these invisible remnants. The Milky Way alone likely contained millions of them, dark, dormant, waiting. But while these discoveries reshaped stellar astronomy, an even greater shock was brewing, one that would expand black holes from a curious endpoint of star death into central players in cosmic history. It began with points of light that did not behave like stars. They were distant, blindingly bright, and profoundly strange. Astronomers first noticed them as intense radio sources, later identifying them as compact objects that looked star-like, but clearly were not stars at all. They named them quasi-stellar radio sources, quasars. When scientists analyzed their spectra, confusion followed. Familiar elemental fingerprints appeared wildly displaced, stretched toward the red end of the spectrum. The implication was staggering. These objects were racing away from us at enormous speeds, carried by the expansion of the universe itself, which meant they were unimaginably far away, and therefore unimaginably powerful. Some quasars were pouring out as much energy as 1 trillion suns, all from regions no larger than a solar system. No chemical reaction could explain it. No nuclear process could sustain it. Even stars pushed to their limits failed the math. Only gravity remained. But not ordinary gravity. The only engine capable of converting mass into energy with such efficiency was a black hole. A supermassive one. Millions to billions of times heavier than the sun, devouring vast disks of gas, turning infall into brilliance. This realization detonated a new idea. Black holes were not just stellar leftovers, they were cosmic engines. If quasars were powered by supermassive black holes, then black holes did not merely exist inside galaxies, they dominated their cores. They shaped their growth. They regulated their fate. Naturally, the next question was unavoidable. If distant galaxies hosted supermassive black holes at their centers, what about our own? The answer lay hidden behind thick curtains of dust and gas in the direction of the constellation Sagittarius. From Earth, the center of the Milky Way was a glowing smear, beautiful but opaque. To peer inside required new techniques, new patience, and an unprecedented sharpening of vision. Astronomers began tracking individual stars near the galactic core, watching their motions year after year. What they found was astonishing. Stars were whipping around an unseen point at tens of millions of miles per hour, completing tight, looping orbits as if bound to an invisible anchor. From those motions, the mass could be calculated. 4 million suns, packed into a region smaller than the orbit of Mercury. Nothing visible, nothing solid, nothing that could be explained away. At the heart of our galaxy sat a sleeping giant, a supermassive black hole, silent for now, yet undeniable. And with that discovery, the story of black holes crossed a final threshold. They were no longer rare oddities. They were no longer theoretical monsters. They were architects of galaxies, and the universe, it seemed, had been building around them all along. With the Milky Way's hidden core exposed, astronomy crossed into unfamiliar territory. The question was no longer whether supermassive black holes existed, but why they were everywhere. Every galaxy examined closely enough seemed to host one, silent or active, anchoring its center with immense invisible gravity. This raised a disturbing possibility. Black holes were not accidents. They were fundamental. When astronomers compared galaxies of different sizes, a pattern emerged that defied coincidence. The more massive the galaxy, the heavier its central black hole. This relationship was precise, almost intimate, as though each galaxy somehow knew how large its black hole should be. The implication was unsettling. Galaxies and black holes did not merely coexist, they evolved together. Yet the logic ran into a wall. Supermassive black holes were too big, too early. Quasars observed in the young universe already contained black holes billions of times the mass of the Sun, formed when the cosmos itself was still an infant. There simply wasn't enough time for them to grow slowly by feeding. Even at the maximum allowed rate, gravity's own brilliance would push material away, choking further growth. This hard limit, imposed by light itself, created a paradox. How did something so enormous form so fast? The solution demanded a radical shift in thinking. Instead of black holes growing gradually from stellar corpses, some scientists proposed that the first giants were born already massive. In the early universe, vast clouds of primordial gas, untouched by metals, unfragmented by turbulence, could collapse directly. No stars, no supernovae, just gravity overwhelming everything at once. In this scenario, the gas spiraled inward as a single structure, forming a dense, rotating disk. The center thickened, heat built, pressure rose. And then, without ever igniting into stars, the core collapsed into a black hole, tens of thousands of times the Sun's mass in a single event. A head start. From there, growth became possible. These early giants fed aggressively, igniting into quasars that reshaped their surroundings. Their radiation heated nearby gas, preventing new stars from forming too quickly. Their jets carved channels through space, redistributing matter across entire galaxies. This was feedback, a cosmic conversation between destruction and creation. Black holes were not just consumers, they were regulators. As galaxies grew, black holes grew with them. When holes became too active, they shut down star formation, stabilizing their hosts. When they quieted, galaxies resumed building stars. The balance was delicate, violent, and essential. Remove the black hole, and the galaxy unraveled. Add one, and structure emerged. But even as this symbiosis became clearer, black holes revealed another secret, one that hinted at their ability to grow faster than any feeding model predicted. They could merge. Across the universe, black holes drifted within crowded stellar systems. Some were born in pairs, others found partners through chance encounters. Over millions of years, these pairs spiraled closer together, losing energy in a way that could not be seen, until space itself began to shudder. When two black holes merged, they did not explode in light. They rang the universe like a struck bell. Ripples spread outward, waves in the fabric of space-time itself, carrying with them a signature no telescope could miss if one knew how to listen. These gravitational waves traveled for billions of years, undisturbed by dust or darkness, until at last they brushed past Earth. And when humanity finally built instruments sensitive enough to feel those tremors, everything changed. The detections were brief, fractions of a second, but they told epic stories. Two black holes circling faster and faster, approaching relativistic speeds, warping space until the distinction between before and after collapsed into a single violent moment. Mass vanished, not destroyed, but transformed into pure gravitational energy. Black holes could grow not only by feeding, but by combining. This revelation solved part of the growth puzzle, but it also introduced a darker question. If black holes merge and grow, if their numbers increase, and if gravity never forgets, what is the universe becoming? Across incomprehensible spans of time, stars will burn out, galaxies will fade, matter will thin, but black holes, those ultimate survivors, will remain, drifting through the cold dark, merging, swelling, dominating the future of existence itself. Some theorists imagine a far future where black holes are the last meaningful structures in the cosmos, massive, silent, and lonely. Others speculate that even they are temporary, destined to evaporate slowly over unimaginable timescales, leaking energy back into emptiness. Either way, black holes sit at the center of every cosmic question. They bend space, they warp time, they challenge the limits of physics itself. And as humanity pushes deeper, building new observatories, capturing shadows at event horizons, listening to the universe's deepest vibrations, black holes remain what they have always been. Not answers, but doors. Doors into regions where reality frays, where the known laws collapse, and where the universe reveals how little it owes to our expectations. The journey to understand them is far from over. It has only just begun. As the instruments grew quieter and the data settled into silence, one truth became unavoidable. Black holes were no longer distant curiosities. They were woven into the story of everything. What began as mathematical speculation had evolved into a cosmic reckoning. Black holes were confirmed not only as real, but as architects, shaping galaxies, regulating stars, and sculpting the large-scale structure of the cosmos. They were present at the beginning, active during formation, and destined to remain until the end. Yet for all that science had uncovered, black holes still guarded their deepest secrets. No signal escapes their event horizons. No information returns intact. Every theory falters at the singularity, where space and time collapse into something undefined. Physics, as humanity knows it, simply stops working there. Equations break down. Concepts lose meaning. The interior of a black hole remains forever sealed from direct observation. And still, the universe keeps whispering. Clues. The detection of gravitational waves revealed that black holes are not static graves, but dynamic beings, colliding, merging, growing. Each merger sends ripples across space-time, echoes of violence that travel longer than civilizations last. These waves allow humanity not to see the universe, but to feel it, turning astronomy into a sensory experience written into the fabric of reality itself. At the same time, telescopes aimed at the centers of galaxies began capturing shadows, dark silhouettes carved against rings of glowing matter. These images did not show black holes directly, but their absence, proof that something with immense gravity was swallowing light itself. The unseeable had left a visible mark. Still, the greatest mystery remained untouched. Why does the universe allow such objects to exist at all? Black holes appear destructive, yet without them, galaxies might never stabilize. They extinguish stars, yet their energy can trigger star formation far away. They consume, yet in doing so, they organize. In this paradox lies their power. Black holes are both destroyers and creators, endings and beginnings folded into the same phenomenon. Even their ultimate fate hints at cosmic irony. Over incomprehensible spans of time, long after the last star fades and galaxies drift apart, black holes may slowly lose mass, radiating away energy until they vanish entirely. If that future comes to pass, then the universe will end not with fire or collapse, but with evaporation into silence. The last light swallowed. The last ripple faded. The last shadow gone. And yet, before that distant end, black holes will continue to challenge every assumption humanity makes about reality. They force science to confront its limits. They demand new theories, new mathematics, new ways of thinking. They remind us that the universe is not obligated to be intuitive, gentle, or understandable. Black holes are not monsters lurking in space. They are mirrors, reflecting how fragile our knowledge truly is. From the quiet orbit of stars at the center of our galaxy to the thunderous mergers heard across billions of light years, black holes tell a single unsettling story. The universe is deeper, stranger, and more powerful than anything imagined before. And as long as there are minds willing to listen, to observe, and to question, that story will continue, unfolding at the edge of darkness where space bends, time slows, and certainty disappears. The journey does not end at the event horizon. It begins there.